Hey, welcome everybody to today's intercontinental seminar on gravity and cosmology. Um, Today's speaker is Lijing Shao, and he is uh, basically from the Kavli Institute for Astronomy and Astrophysics at Peking University. And he did his PhD at PKU, and then at 2018 he joined PKU as an assistant professor. And just recently, about a month ago, he became an associate professor. And first of all, thank you very much for joining us and giving us this talk. And with that, I hand over to you. Please start your screen sharing and start your talk. And for the questions, it's okay when the speakers, with you, when the people ask questions during your talk, or do you prefer it afterwards?
Yeah, they can ask a question anytime.
Okay. I monitor the chat, so if you want to ask the questions during the chat, I will check there regularly. And please start your screen sharing.
Okay. Can you see my full
With
screen?
that, I hand over to you.
Okay. Yeah, I will turn off my video. Yeah, just for a better connection. So thank you very much for the organizer for inviting me to give this talk on astrophysical test of bumblebee black holes. So this is actually based on a series of work that we have done recently in our group, and it's a very good opportunity for me to share this work with you. And if you have any question, just stop me and ask straightforward. And if you prefer to ask afterwards, that's also okay. So this is some work we have done mostly last year with a couple of group members. So here is Dr. Xu Rui and Dr. Liang Dicong, and also Dr. Mai Jiangfeng, and also a PhD student of mine, Hu Zexing. So basically, we found the black hole solutions in a class of vector-tensor theory called the bumblebee gravity theory, and then use these solutions to put a constraint using the astrophysical observations, including black hole images and extreme mass ratio inspirals. And also, we did some prediction for radial pulsars around the Milky Way supermassive black hole in the center of the Milky Way. We also did some theoretical work to investigate the dynamic instability of the theory, because as some of you know, when there is a vector field in a gravitation theory, there maybe have some unstable modes. And actually, we have also done some other work on gravitational waves and thermodynamics and also cosmology in this bumblebee gravity theory. But I don't cover these in this talk. But if you are interested, you are very welcome to take a look at these papers. So this is our focusing point of this talk. So we start with this action. This action actually has some interesting features in this action. So for example, this red term, this is a non-minimal coupling between a vector field B mu to the Ricci tensor R mu nu. And also we have a normal kinetic term, and this extra kinetic term, and a potential term. So this bumblebee gravity theory actually was an illustrative example in a field theoretical framework called the standard model extension, which is a very extensive framework incorporate the Lorentz violation, the Lorentz symmetry violation into the gravity and particle physics. So if you know this theory, there is some correspondence with this gravity bumblebee coupling and the some field in the SME. This is standard model extension framework. If you are not familiar with this this extension, it's also okay, because this is the only place that I mentioned this this correspondence. Just to show this bumblebee gravity theory has a wider context in the formulation of gravity theory. So this green term here, characterized by this beta, is actually immediately show some ghost mode even in the Minkowski space-time. So later on, we will drop this term for now and only focus on this red, this non-minimal coupling term. And this potential term here it's basically you can have any kind of potential for this vector field, and it will produce some non-vanishing vector field via the minimization of the potential. It's similar to the Higgs mechanism in the particle physics. This is called the non-zero vacuum background solution for this B field. And we will include this sum of effect from this potential term. So there are a bunch of work actually starting from 1960s to up to now. They work on this extension of the Einstein-Hilbert action, and by including this non-minimally coupled vector field. Okay, so from this action, actually, it's a standard the textbook derivation. You can get the field equations. So this is the field equation for the metric field. This is the field equation for the vector field, and there are some extra terms. And later on, we will simplify this field equation by ignoring this blue term here. This is because we want to investigate only some vacuum solution. So we will set this T mu nu of matter to 0. And also because this potential, as I said, it provides some mechanism to minimize the potential by providing some Lorentz violating field. And after this is the slope of the vector, and it vanishes at its equilibrium point. So later we will deal with such a theory to find the solutions to these field equations. So after this simplification, we have this somehow simplified the action with this non-minimal coupling term and this kinematic term and also some potential term. This is the starting point of all these all of the following work in this talk. So actually, there was a paper by Kasana et al. They discovered a very elegant solution to this action. So this is an exact Schwarz-like solution in the bumblebee gravity model. So as you can see, this is the line element of this solution. As you can see, it's very, very close to the Schwarzschild black hole solution. The only difference is here is this air here in front of this GRR term. This air is actually the C parameter, which is the non-minimal coupling parameter with this B square. B square is the non-vanishing radial component of this B field. This is actually a very elegant solution, and it is very easy to verify. This is one of the correct solution of the field equation. You can just plug this equation into the field equation that I was showing in the previous slide, and to check this field equation, they are satisfied. So this is very nice. This actually triggered our following up work to derive a complete set of solution to the field equations. So here is our starting point. So our goal is to have a complete set of vacuum solution of the bumblebee gravity theory with spherical symmetry. So this is the most general way to write out the line element and also the B field with spherical symmetry. So here we have some functions, which is the mu and nu, and also this bt and br. They are functions of the radius only, and this is the line element for for the most general spherical symmetric space-time, and we want to solve these unknown functions and get the complete set of the solution in this bumblebee gravity. So actually, we achieved this goal. And first, I want to show a subset of this solution. So which is some extended analytical solution to the field equations. So as I show them explicitly here, you can see we have solved this mu and this new function. They are actually very similar to the Schwarzschild case. And we also solved this BT. BT is characterized by two free parameters, lambda 0 and lambda 1. And BR is trivially given by some algebraic expression, which is it's quite simple, but it's exact solution here. So in this analytical solution, there are four integral constant, which is this parameter m, and this parameter mu naught, and the parameter lambda naught and lambda 1. So this BR is, if you fix all these parameters, this BR is given by this expression. So this solution, as you can see, it's an extension of the previous solution. We can see it by this. So if we set this B lambda and this lambda 0 and lambda 1 to 0, we exactly recover the Cassana's solution in 2018. And if we set this mu naught to 0, if we set this mu naught to 0, this is 0, then you can see this mu and this nu, they give the line element of a Schwarzschild black hole. So, but we can still have this B field. This is very interesting. It's a Schwarzschild space-time, but with a non-trivial B field, which is actually contributing to the T mu nu part. This actually is a solution also found earlier by Fan in 2018. And further, if we set this mu naught to 0 and further set m to 0, this m is here, and you can see this line element, this mu nu, it becomes 0, and it recovers the Minkowski magic, which is a flat space-time. But there is still this B field. But this means we can have a flat space-time with a non-zero vector field. And this vector field is contributing T mu nu, which curves the space-time. And but in the meantime, the repulsive force of this vector field actually balances the gravitational contraction, and it achieves eventually a Minkowski space-time. Okay, so this is an analytical solution that we found with four integral constant, and it covers the previously known result. But this is not the most general solution yet. So for the most general solution for this field, for this field equation, we actually cannot get analytical solution, but we can get a numerical solution. So we, based on the field equation, we give recurrence relations for these coefficients. These coefficients actually are expression of expansion of our unknown function as a function as a Taylor expansion of this the power of R. Okay, so this we can achieve this recurrence relation for this mu n, and lambda n, and actually we found we found this recursion relation, and by plugging them into the field equation, we can find two families of horizon solution. So by saying horizon, I mean for this solution, this GRR diverging at a finite radius. This is our definition for the horizon, but this is not a black hole yet. they are just a horizon solution. I will talk deeper to black hole solution at some later slides. Okay, the two family of horizon solution, they are characterized by this. So for the first family, there is the BR, the radial component of the vector field equal to 0. In this family, we have only three parameters, three free parameters. The other parameters, this higher order, these terms, they are actually explicitly given by the recurrence relations. And the other class of solution has some vanishing RR component of the Ricci tensor. And in this class of solution, we have 5 free parameters. And the other higher order free parameters, they are given by the recurrence relation that I couldn't show here, but they are fixed after we give this 5 free parameters. So what happens here is because in our derivation, we found the product of this BR and this RR component of the Ricci tensor equal to 0. So this branches into 2 branches. So one is with this solution, the other is with this solution. So we can derive all the horizon solutions in this bumblebee gravity theory, which forms actually a complete set of horizon solution with spherical symmetry in this bumblebee gravity theory. So we wanted to investigate what are these solutions in somehow detail. So before that, we also considered the conservative quantities, which you can of course get via the Northern theorem. And there are 2 conserved quantities. One is the conserved current. So this is the common mass, because we are not necessarily have a asymptotically flat space-time. So this is the common mass instead of ADM mass. So this is given by this Killing vector, and we can have expression here. And using our coefficients, it's basically this term. Okay, the other is the bumblebee charge. Bumblebee charge is also a conserved current, and it's given by somehow this expression here. Here, kappa is equal to 8 pi times the gravitational constant. So these are the 2 conserved quantities in the solution. So speaking of the horizon solutions, so here I show the horizon RH in the family that I showed before with the radial component of the vector field equal to 0. So here in this family, as I said, we have 3 free parameters. So here I plot this RH in unit of mu1. So here mu1 is chosen as a unit. So we can have the plot here, show here. So each plot shows the horizon as a unit of mu1 in this lambda naught and the lambda 0 and the lambda 1 plot. So this colors shows the value of the RH in unit of mu1. So as you can see, when we have different Kc value, here's Kc, here's Kc, have different Kc value, which is the non-minimal coupling constant. We have different behavior for the horizon distance, or for the horizon radius. Okay, so one of the important interesting point is that when this Kc equals to 2 kappa, and there is a line here in this figure, it gives the Schwarzschild metric, which is the solution that I showed before, that when you have a non-zero vector field, but you still can have a Schwarzschild metric. But they are not a black hole yet. They are horizon solution. So if you remember, by saying horizon solution, I mean GRR diverges at this value of RH, this horizon radius. But if we further impose that GTT at this radius equal to 0, then we call it black hole solutions. So which is very similar to the Schwarzschild case. Simultaneously, we have GRR diverges and GTT goes to 0. So this actually gives some lines here, which if you can see here, there are some brown curves in this plot, in the plot I showed before. And these are the solutions of black holes, which have the a diverging GRR and a vanishing GTT. So this gives so basically what I have said up to now is that we have found a complete set of the horizon solution, and of course if we put a more constraint, we have the complete set of the black hole solution in the bumblebee gravity with the spherical symmetry. So later we wanted to use this solution to see if they satisfy the observations. So in this, if we have already demanded this black hole solution, we have this mass goes to this simplified expression, because in this case the space-time is asymptotically flat. This also have charge. This is related to lambda1 and mass related to mu1. This is some very simplified calculation. So in this case, we also wanted to investigate this behavior of the horizon radiance as a function of the bumblebee charge. So as we plot some representative case. Hey.
I think Theo has a question.
Yeah, hi, please.
Yes, sorry for interrupt. So in the solutions where GTT is not 0, but GR diverge, are they wormholes?
I will mention that in a later slide. But
okay.
The answer to this is we don't have a clear idea yet.
Okay.
This is my answer from from our team, but we are still working on this. But I will mention it in some later slides.
Okay, thank you.
Yes, thank you for your question. So in this plot, so we show that a different representative case for this this RH horizon radiance and the Q relations. So as you can see, when Cassis is smaller than 0, for example, here is this blue curve. So we have Q max is smaller than M. This is the case, and of course, if Qc equal to 0, it goes directly to the Einstein-Maxwell theorem, and it gives Rn black hole, which is given by this orange line, which of course by the cosmic censorship principle, we cannot have this charge larger than M. And if we have Cassis larger than 0, we have okay, you can see here for this, for example, this red curve or brown curve and so on. They can have this bumblebee charge larger than M. So this is an extension of this Rn black hole with this non-minimal coupling. And there's also some interesting thing I show here. So when this Cassis parameter, this non-minimal coupling parameter, is smaller than 2 kappa, our horizon radiance is always smaller than 2m. And this is the special case I have already talked about. If Cassis equal to 2 kappa, we get exactly Schwarzschild black hole solution in our bumblebee gravity theory. And on contrast, if Cassis is larger than 2 kappa, we get the horizon radiance larger than 2m. So goes back to Chiu's question. So we have also solution that GRR is divergent, but the GTT is non-zero. We try to look at the behavior of particles and waves of this solution, and we found the following behaviors. So here in this plot, I show this x, y, this coordinate, and this black circle shows this this is the horizon radiance of one of such solution, which we call CH, which is the abbreviation for compact hairs. This is the black circle, and the black disk gives the horizon, the Schwarzschild radiance. And you can see here, this is the geodesics of test particles, and the solid line, this orange and this blue lines, solid lines, they show the geodesics of the compact hairs. And the dashed lines, this is the dashed line here, they show the geodesics of black holes. But the black hole solution, as you can see, these geodesics end at the horizon and then falls into the black hole. But for these compact hairs, actually, we can analytically show that these geodesics bounces at the horizon radiance. So they have bouncing geodesics because these geodesics, they have velocity exactly equal to 0 at this point, but the acceleration is outwards. So which means these test particle geodesics, they are bouncing. And actually, we don't quite understand this behavior. We can have this geodesics, which is calculated rigorously, but we don't actually have quite a clear physical meaning of this solution. So we suspect maybe this has some relation with the gravitational-wave echo, but this is our suspicion at now, and we don't have any proof that our this compact hair solution can produce the echo or not. But it's maybe this can have some kind of echo behavior. And we did some preliminary calculation for waves because on the previous slide we only show the geodesics for test particle, and we also calculated the refraction and absorption of the compact hairs. And there is some promising features that may be result in the echo, but we are not sure about this yet. It's still under investigation. So I hope I answered your question here for these solutions. So later we focused on the black hole solution only, and we wanted to see if these black hole solutions, they are consistent with the observation. So first we consider the perihelion advance in two families. So this is a family with BR equal to 0, and this is some complex expression, but this solution, if we look at it carefully, this solution only depends on the B field. This is BT field. This is BT component, the temporal component of the B field. And on contrast, for the other families, this is the RR component equal to RR component of the Ricci scale of the Ricci tensor equal to 0. This case, this is perihelion advance rate only depend on the space-time metric. This is mu. This is a function for the space-time metric. So this is our calculation for the perihelion advance. And we compare this calculation with the observation of the 4 planets, the Mercury, the Venus, the Earth, and the Mars. So these are the results for the 2 families. So for the first family, actually we found if we impose this 2 lines enclose the measurement uncertainty, and this common region shows the viable parameter space for the theory. So if we look at this family, we found actually the viable parameter space is very tightly limited. Here you can see the value is 10 to minus 11 already. So later we don't investigate this family because they are very tightly constrained already. But on contrast, for the other family, for this family with the radial component of the vector field vanishing, this family, we found the perihelion advance impose a very weak constraint on the parameter space. So this is still a viable theory with larger parameter space that survive the test of perihelion advance. So we are very interested in this family of the solution, and wanted to see further if this can result in some interesting behaviors. So we consider the black hole shadows because our solution is exact and can apply to the strong field. So we consider the angular diameter of black hole shadow, which is this D is angular diameter of the parameter of the black hole shadow, and this actually depends on these 2 parameters. One is theta g. Theta g is simply the mass of black hole divided by the distance of the black hole to our telescope, which is this definition here. And the other parameter is the critical impact parameter, which is the sigma LR. LR means light ring here in the unit of the mass.
And Lijing, there's another question.
Yeah, please ask.
Hi, Lijing. Can you hear me?
Yes, I can hear you.
Can I ask a question related to your the bounced CH solution?
Yeah, sure.
In previous slides, I mean, does your compact here solution have anything to do with, or anything, any dependence on your bumblebee charge or something like that?
Yeah, the detailed behavior depend on the bumblebee charge. For example, how large is this horizon radiance and so on. But this quantitative behavior does not depend on the bumblebee charge. So for all bumblebee charge, they have this kind of behavior.
Do you mean even the charge is very small, very tiny, as long as it's not zero, it still have this
yes,
bouncing,
they have these bouncing geodesics. Yes.
Okay.
As long as they have a diverging GRR but a finite GTT.
Yeah, I think maybe this has something to do with the bump field because it's a vector field, but it seems not so simple.
Yeah, so we just have discovered this bouncing geodesics in this solution. Yeah.
Okay, thank you.
Yeah, thank you for your question. So I will continue with the with this. So this this is equation here. Simply, this is a very simple equation gives this theoretical value of this sigma LR and the relation between this angular diameter and this theta g. So actually, in reality, we can measure actually the event horizon telescope calibration. They can measure this d and this have some other information to get this theta g. So which means if we, in theory, we calculate this sigma LR, this light ring critical impact parameter, and we can test the theory because we can measure this d and this theta g for at least for two black holes, this M87 star and the Sagittarius A star. This is a measurement from independent measurement of these two parameters from this event horizon telescope calibration. So we impose this measurement and try to see what we get in terms of the bumblebee charge and via the constraint on this theta LR. So this is the result. So here I show the theta LR as a function of the bumblebee charge. So this blue region shows the result come from the M87 star. This measurement of the sigma LR by using the above equation I showed in the previous slide. And this orange-ish band gives the constraint from the Sagittarius A star, which was published 2 years ago. And as you can see, the Sagittarius A star gives a tighter constraint. And for this, and if you see this, the projection here, it constrains the bumblebee charge to the region around the older one. So the conclusion is the black hole shadows give constraint on the bumblebee charge to older one from these observations. So actually, we can also investigate some part of the parameter space, which is excluded by the gradient instability. But these are very small spaces. I will not talk it in detail here, but we can also exclude some parameter space, which is actually similar to the constraint from this orange and green lines. This is the two black hole constraint. And we can also exclude some parameter space using the instability argument, but I will not go to detail here. Yeah, but the overall conclusion is this both the instability and the black hole shadow observation, they give older one constraint on the bumblebee charge. So So because the constraint is older one, it's not very tight. So we want to see if future observation will give tighter constraint. So we consider the extreme mass ratio inspirals, so abbreviated as EMRIs. So which is a type of gravitational wave source for space-based millihertz gravitational wave detectors. So which these are one supermassive black hole, and there is another small compact object is orbiting around this supermassive black hole, and they emit gravitational waves and can be observed by millihertz detectors. And we consider if this central supermassive black hole is a bumblebee black hole instead of a black hole from GR. So what kind of observation? This observation can put what kind of constraint on the parameter space. So this is our calculation. So in our calculation, we found that the geodesics of the the small compact object changes with respect to the EMRIs in generativity. And also the energy loss rate is also changes. So which result in the overall dynamic changes in this EMRI systems. And we consider some example EMRIs. We have this 10⁶ solar mass and with 10 solar mass black hole, and at some typical distance is 100 MPC. And we're starting the evolution of the system at 5 Schwarz radians. And so initially, this waveform, they are very well aligned. But after some, let's say after 1 year, they have significant phase difference, so depending on the bumblebee charge. So here I give 3 curves, which have different bumblebee charge. And they have some defacing with respect to each other, in particular with respect to the generativity. And this defacing actually is very crucial for the space-time detectors. And the space-time gravitational wave detector, they can detect this defacing effect. So we made this. This is just one example, and we looked at the whole parameter space and try to find what kind of phase difference we can have after 1 year of this kind of system and in the parameter space here. So this dashed line here, we just show some threshold value for the defacing, and we can see if we can measure this threshold defacing, we can constrain this bumblebee charge at the level of 10 to minus 3, which is 1,000 times improvement over the measurement from the black hole shadows. So this is the projection for the LISA type detectors. So we also checked it with another technology. It's called the faithfulness calculation, which basically calculates how the 2 signals looks alike by maximizing some reference time and reference phase. And this expression shows how S1 looks similar to the S2. And there is some criteria, some threshold for the
Lijing,
sorry, yeah,
has a question.
Yeah, please ask.
Hi, Lijing. I have a question about your previous slide.
Yeah.
Or more about the system in general. I mean, first of all, does an EMRI that is 5RS at the start even survive 1 year in band before plunge? Because this seems to me like a very extreme and idealistic case, let's say. Assume that the EMRI is that close at the start. And then a second question related to that is this, let's say, phase shift that we get from the bumblebee black hole. How does it compare to the, let's say, phase evolution you get? Because like when we're very close to merger, the frequency of the EMRI is evolving very fast, right? So I'm wondering like if this is really like of the same order or bigger or smaller.
Okay, thank you for your questions. So first, this is just showing one example with some typical values for this parameter. which we just evolved for 1 year, and to see how this phase difference develops for this. And this actually, as you can see, this is some unit here in the unit of second, and this is kind of cycles. And the one period is about 500 seconds, and then evolve for 1 year. Then we have like half a circle phase difference for this this particular example. Yeah. So this is I mean, this is a small phase difference compared to the overall phase evolution, but this is still according to the study team of Lisa, it's still some measurable phase difference, which is like a pi or something. Yeah. But because this is just calculated the phase difference, so we wanted, you know, in the next slide, we wanted to check with the faithfulness calculation, and we found a similar, you know, consistent result. So this shows the calculation is somehow well estimated. Yeah, did I answer your question?
Yes, thank you.
Yeah, thank you very much. So by calculating this faithfulness, we put the typical threshold for this faithfulness for a typical, you know, signal with SNR equal to 30. We also get the constraint on this Q at the level of 10 to minus 3, which shows here. If Q is too large, we can already show this faithfulness smaller than this value, and this is consistent as the previous phase difference calculation. There is some small difference, but the overall is consistent. Okay, this is one type of future observation we can think of, and another type of observation concerning the radial pulsars. So we are looking for, actually, internationally there are a few of teams. They are looking for a pulsar orbiting the Sagittarius A star, the central black hole at the in the Milky Way, and they try to look for a pulsar orbiting close enough to the black hole with the orbital period smaller than 1 year. So if such a pulsar is observed, they can timing it via the technology of pulsar timing, and pulsar timing is very precise, and it basically measures the times of arrival at the radio telescope, and then compared to a model, for example, a space-time model for the Sagittarius A star black hole. And if the Sagittarius A star is a bumblebee black hole instead of a black hole in general relativity, they will produce characteristic signals in this pulsar timing. And unfortunately, for now, such a pulsar is not found yet, but it is on the list of the key science project for the square kilometer array, the next generation radio telescope, which is currently under construction, and we will finish the construction for phase 1 in 2027, which is 3 years from now. Okay, this is one of the science goals, and we wanted to see if such a system is found, what kind of constraint we can put on the bumblebee charge. So we calculated the orbit of the pulsar around the Sagittarius A star. So here we just take an example of a half a year orbit pulsar around the Sagittarius A star, and we assume we observe such a pulsar for 5 years, which means roughly 10 orbit. And because of this massive black hole, the orbital process, and you can already see the precession here, which is in the unit of millipc. Millipc is 10 to 13 meter, and in pulsar timing we have timing precision of microsecond. Microsecond times the speed of light, which is roughly 300 meters. So we have a timing precision of 300 meters, but here the difference can be as larger as 10 to 13 meter. So which means that we have a very, very good precision to measure the orbit here, And however, there are quite a few parameters to be inferred from solely from this time of arrival. And we carried out a numerical study of this orbit and plus construction a timing model to fit globally all the parameters in the timing model and try to see how the parameters are correlated and how these parameters, the precision of these parameters can be measured. So this is what extensive numerical study we carried out with the radial pulsar around the Sagittarius A star. So this is our result. So we show for 3 different coupling constant, and we can see we can based on the orbital period of the pulsar. So previous slide I just showed one example of 0.5 year orbital period, but we can do simulation for different orbital periods. And by this and using the parameter estimation program we developed, we saw that we can basically also constrain this bumblebee charge to the level of 10 to minus 2 and to 10 to minus 3 at this level, which is a little worse than the MRIs, but similar, comparable to MRIs. This is the bumblebee charge we can measure with the pulsars around the Sagittarius A star. This is also a very good science target for the SKA like telescopes. Okay, so here go to my summary. So let me summary what I have talked about up to now. We found 2 families of non-spinning black hole solutions in the bumblebee gravity model. This is actually a complete set of spherical symmetric bumblebee black hole solutions. And these 2 families, they are characterized by 2 different conditions. One of the family, which is the radial-radial component of the Ricci tensor equal to 0, this family is very tightly constrained by the perihelion advanced observation in the solar system. So we don't consider this family further. And the other family is already weakly constrained by the EHT black hole images and also the consideration of instability. The gradient instability to be specific. These are considered to be older unit, the bumblebee charge. And this is the current best constraint on the bumblebee charge. But for the future, we will have MRIs and radial pulsars. These measurements are so precise, and they will tightly bound the bumblebee charges to the level of 10 to minus 3. So this is basically the end of my talk. Thank you very much for listening.
Thank you very much, Lijing, for the talk. Are there any questions?
Maybe I.
I don't know in Oldenburg who has the question, so maybe just unmute yourself and ask your questions.
Open the video.
Yeah.
They can see.
Yeah. Thank you very much for this interesting talk. I would like to understand better what the constraints are that you have for the potential.
For the potential, yeah. Yeah, this is a very good question. The potential here, basically, we don't put a constraint from our calculation. So this is a potential term, which basically, in our calculation, we assume the potential is steep and provide a vacuum value for this B field. And this is our assumption. It's also a commonly used assumption in the standard model extension. And of course, this potential is not infinitely steep and will have some curvature and the slope and curvature. And this will produce some other effect. For example, the value of the potential itself will provide us some cosmological background, like the cosmological constant. So actually, in the field equation, it plays the role of cosmological constant, which is at a larger scale, at a larger than GPC and so on. So we don't consider this larger scale dynamics, but it's an interesting question to consider. Actually, we have some work in progress to consider the cosmology in this bumblebee field theory, but we haven't got a very systematic result yet. So it's it's in progress. And in our localized systems, we just have ignored this larger scale effects. Thank you for your question.
Yeah, thanks a lot for the answer.
Thank you.
Okay, Shao?
Yes, thank you, Lijing. Very nice choice, very clear. So just a comment about the compact Hill solution. So I think one way to check whether the solution is wormhole or not, I think it is, maybe you can use the you can check whether the solution satisfy the Morris-Thorne wormhole expression. So in that expression, the GTD components diverge at the throat, and the GR component diverge at the throat, and GTT is finite there. So I think you can check whether, for example, the Ricci, the curvature invariance is regular or not at the throat, and then whether the flaring out condition is satisfied there at the throat. If everything is satisfied, I think it is really a wormhole.
Yeah, thank you very much for your comment. Yeah, it's very valuable. Yeah, we will take a look at this. Thank you.
Thank you.
Michael?
Hi, Lijing. Very nice talk. I have maybe a similar question to Zhe, but my question is more like, does your black hole solution singular or not? Like in general, does it have the singularity or not? I mean,
yeah. So this is a very good question.
Model.
Yeah, this is a very good question. But up to now, we only have calculated the matrix, up to the horizon radiance. So we didn't calculate the solution inside the horizon radiance. But it's a very interesting question.
Okay.
Yeah.
Thank you.
Thank you for your question.
Okay. Yao?
Hi. Thank you very much for the talk, Professor Shao. I would like to ask how many degrees of freedom there is in your in the model.
So in the model, you mean for example, this is the action we have. So can you see my screen actually?
Sorry.
Can you see my screen?
Yeah. Yes, I can.
Yes.
Yeah. Okay. Yeah. So this is the action we have. So in the action, we later we drop this potential term as I explained earlier. So we just only have one theory parameter. This is this non-minimal coupling C. So this is from the theory side. And later we have field equation, but field equation, you have to integrate the field equation, which introduces the integration constants. Well, then we have like the three free parameters in one of the family and so on. Yeah, these are the integral constant. They are not a theory parameter. The theory parameter, we only have one. It's this non-minimal coupling here. This is a C parameter.
C is a field or just a time parameter? Depends
so here,
on
C is just a constant parameter. A constant
parameter. Okay. It's not the field.
It's not.
Okay. In fact, I'm asking not the number of the free parameter in the theory. I'm asking the propagating degrees of freedom in the field. Yeah.
Oh, that's also a very good question. Actually, we have calculated this. Actually, we published a paper in 2022 by investigating the number of degree of freedom in the theory. But in this theory, we found the following conclusion. So the number of degree is not fixed, depending on how you violate the Lorentz symmetry.
Yeah.
we can have 2 degrees of freedom up to, if I remember correctly, up to 5 degrees of freedom. And there are also some interesting mixing with these different degrees of freedom. It's some new phenomena we found in this theory. Yeah.
And depends on which parameter, the number of the degrees of freedom.
Depend on the actually because let me explain in some detail. So because in this V potential gives a fixed background, depending on how this angle aligns with the B field.
Time-like or space-like.
Yeah, exactly.
Yeah.
So we have different numbers of degree of freedom.
Okay, you mean from 2 to the 5, depends on the.
Yes.
But there's only 2 options or 3 options, time-like, space-like, or no, like. So you mean
we didn't consider. I only remember we consider temporal component and the radial component, and we don't consider this light-like curves.
Yeah, I mean, so which so each different cases corresponding to which number of the degrees of freedom. For example, in the time-like.
I don't remember it off my hand. Sorry. So the paper is here. Actually, I have listed here. This is the paper here on the gradual waves. We consider the Wakefield limiter and the propagation of the propagating degree of freedom in this paper.
Okay. I suppose you mentioned that because you mentioned the dynamic instability analysis in the last paper.
Oh yeah.
Okay.
Yeah. That's
okay. So it's very interesting. And okay. Thank you very much.
Thank you for your question.
Maybe I have another question. Like at first few slide, you mentioned you can have a solution which is in Minkowski, but the vector field is not 0. But how can this be possible? Because the vector field will also contribute to an energy momentum tensor, or not?
Yes, it
Then
will contribute
really
to. Yes, this is actually very interesting. It will constrain this vector field will constrain to the T mu, and which of course curves the space-time. But in the meantime, there is a repulsive like force because of the vector field. It balances off the curvature, so which gives exactly this flat space-time.
Okay. Thank you.
Yeah, it's quite interesting. Theoretical of academic interests result. Yeah. Thank you for your question.
Okay, if there's nobody who has a question right now, maybe I can ask a question. You mainly focus on like spherically symmetric and static spacetime, if I saw it correctly, or like the equivalence. Do you also plan to work on rotating spacetimes, like or better rotating black holes?
Yeah. So the spherical symmetric spacetime is simpler, and this is so our first step. We have worked out this. And there are also some other groups. They follow up our work and work on the slow rotation limiter for the curl-like spacetime, but only with slow rotation. We assume this spin parameter is a small quantity. They have got some result, and to have a general, without this slow rotation approximation, we didn't find the solution yet because the differential equations, they have become the partial differential equation and hard to solve and hard to get a complete set of the solution in without this spherical switch.
Oh. So are there any other questions? If not, I would say we end the official part here and go to a more free discussion, which would be depend on also on Lijing how much time you have.